So this is a project about tracking of wildlife. And I guess it's really a technical project because it's a project about the development of a new type of tracking tag. So this is an example of one of them here. Most of the smarts are hidden behind a little metal shield, but there's one here where you can see that there's a little bit of electronics in there. We developed this as part of a project to try to understand how New Zealand's seabirds use the ocean around New Zealand, which is quite wild and involves very long distance travel. And so once the Royal Albatrosses, which we were tracking, once they leave land, we have no idea where they go. So this project involved both the development of this new type of tracking tag, which operates in a strange way. It doesn't know where it is. It's like a little black box flight recorder. It captures a little bit of the signals from the GPS satellites for about 1 millisecond, stores that data, and goes to sleep. So it uses very, very little power. And this project involved, well, I guess about 15 albatrosses that were tagged. And each one ran for an average of 3 or 4 months. So this data that we've got shows all of the movement of the albatrosses. It shows every fix that we received, and there were tens of thousands of them. As you will see throughout the data, when the albatrosses, perhaps they dived a little deep, they do dive underwater, or perhaps the tag's casing just failed because it wasn't particularly well sealed, the track will stop. So that's all this is really, is the data from that project. The fixes are just overlaid over a map of the Southern Ocean, and you can see behind each albatross is a little tail, which is the fixes that albatross had over the previous 5 hours. So each dot on the map is a little moving tail showing how the albatross has moved. And the tail really just makes it a little easier to see how quite complicated these paths are. So the other thing we find is that the albatrosses travel both at day and night, which is quite impressive. People have argued perhaps they use the stars to navigate, but down at these latitudes, the stars are only occasionally visible. Maybe one day in every 3 or 4. And they travel regardless of the weather. So they're out there and they're working day and night. The animation you see has a very slight change in color between day and night. It's barely visible, but on the top right, we've got the date and the time, and so those are New Zealand time. So when it's AM, it's New Zealand morning time, and when it's late in the evening, it's New Zealand evening time, and it's pretty dark. This was in summer, so the days are quite long. The thing that we find amazing is that the albatrosses can hang around the continental shelf. Yet the ocean on one side of the continental shelf is maybe 200 meters deep. It's pretty deep. On the other side, it'll rapidly drop. In the space of a few kilometers, it'll drop down to about 1 kilometer deep or more. Yet the albatrosses seem capable of flying over the surface of the ocean and hanging around exactly where the continental shelf is. Perhaps it's food, perhaps there's something they can sense, smell in the water, something that's different. But we don't really know how they do it. It's not easy in a boat to locate the continental shelf, particularly in rough weather, and the albatrosses can do it in pretty much any weather. When you get the tag back, which you have to do in order to figure out where it was, you then have to process that data, and it's a bit of an epic processing job. It takes 1 millisecond to capture the data. It takes us about 5 minutes on a very fast computer to work out where that tag was when the time the data was captured. But because it only operates for a millisecond, it's very low power on average. So it'll take a fix every 10 minutes, but it's only really on for a millisecond or 2 every 10 minutes. So it might be 10,000 times less power than a normal tag. That means you can run them for months, capturing data quite often. So this data shows another thing which we think is amazing, is that every now and then one of the albatrosses will take off from Tyro Head and decide to travel to one of the more distant offshore islands, Bounty Islands to the southeast of New Zealand, or Chatham Islands. And this isn't just an isolated thing. You know, here's another one, long flights, straight lines, weeks spent at sea, and then returning home without fail to what is a pretty hard thing to find if you're 1,000 kilometers away downwind. They don't wander there, despite the idea of a wandering albatross. They fly in straight lines, and they fly in straight lines for days over close to 1,000 kilometers. And that's an amazing feat of navigation. If you imagined being on a boat without a GPS system, to track through stormy waters in windy conditions for 800 kilometers in a dead straight line on the map is really pretty impressive. And no one knows how they do it. How can they locate themselves? Then, once they're there, they'll spend 2 weeks perhaps hunting for food. We don't quite know what they're doing, but they spend a couple of weeks in that spot. And then they'll head straight back to Tairoa Head, which is where they're based. And that's another feat of navigation. How do they get back? How do they, against the fact that the wind has now changed? While they're flying, the wind changes, yet they still keep tracking a straight line, and they come back. What are we going to do with this data? We'd like to try to understand how, quantitatively, from the analysis of these tens of thousands of fixes, how the albatross could be locating the continental shelf. At a simpler level, we can understand from these feeding flights. These were flights where the birds have a chick on the nest, and so they spend only a couple of weeks going out and visiting all the places which might be quite bioproductive. So in a way, their movement can be a marker for how productive each of the regions of the ocean around New Zealand is. And there's an ongoing effort to try to use wildlife movement to understand more about the environment. The other thing we'd like to do is attach more sensors to the birds. We don't know a lot about other conditions that are around. For example, it might be that the temperature, which we can sense, but we're not recording, we haven't recorded it from this data, but the temperature affects how they move, whether they perhaps are able to track the continental shelf by changes in ocean temperature. We don't know any of these things, but it'd be fascinating to find out.